Hello everyone, I'm Julia Maia. I'm a first year PhD student at Lagrange. I'm on the planetary science team, the top team, and I'm working with my supervisor is Mark Vixorek. So my PhD project is about the internal structure of Venus. And in this talk, I'm gonna, since most people probably never had a talk, listened to a talk about Venus, I'm gonna go through the history of Venus exploration, talking some of the main findings and some of the most important issues, and how my project kind of fits into all this. Okay, so here I'm showing the 5 what we call terrestrial planets, actually the 4 terrestrial planets plus the moon that we normally put in this mix because it's a very well studied planet with a very complex geology, although it's not a planet we put in this group. And what we can clearly see in this figure that has the sizes are roughly to scale and the distances as well, is that Venus is the planet that has the most similar distance to the sun at the Earth. It has it's a distance of 0.7 AU. Also, the size of Earth and Venus are very similar, and the masses of these 2 planets, so the composition of these 2 planets are very similar. Another thing we can see is that all of the bodies except Venus, we can see the surface in the visible domain. So, and on Venus, we cannot see that because of its thick atmosphere and because it's globally covered by clouds. So here, as a person that likes geoscience and works with geoscience, I prefer looking at the surface, but this is not a real figure, a real image. It's a mosaic of radar images, and I'll talk more about that later, how we map the surface of Venus. So because of the similarities between Earth and Venus, we call these 2 planets the twin planets. And although they are similar, they have very important differences. And because of the thick atmosphere of Venus that is mostly CO2, the surface temperature of the planet is 470 degrees Celsius, and the surface pressure is above 90 bars. So it's a good example of what happened when you start putting a lot of greenhouse gases in the atmosphere, like we're doing. So another important thing is that Venus does not have a measurable dynamo. So we know that around Earth, there's this active magnetic field that is generated by this in its core, and in Venus, we do not see this activity. And another important aspect is that on Earth, we know that what drives the geology and what's the main mechanism of heat loss that comes from the interior of the planet is plate tectonics. And this, we do not see this on Venus, although Venus has tectonism, it has faults, it has folds, it has mountains that shows that there is some tectonism, there's no plate tectonics, and we are not quite sure what kind of, how this planet loses its heat. And another very important thing about Venus is that its surface, like on Mercury, on the Moon, and on Mars, we have very old surfaces that are full of craters. And on Venus, we only mapped, there's only around 1,000 craters. It's very little. That indicates that the surface of Venus is very young compared to these other planets, and it has a similar age to the surface of the Earth. So Venus is somehow have a resurfacing process that is not plate tectonics, and we do not know what it is. So a very important question about Venus is, what are the geological processes that make the surface of Venus so young? And another important thing is that resurfacing process is something that happens kind of continuously throughout its history, or maybe something that was a catastrophic event that completely resurfaced the planet. That's another possibility. And in this sense, the early Venus, a Venus that maybe from before this possible catastrophic event, what is very different from what we see this hellish planet now? Was it a habitable, water-rich world? And maybe it was, because from some atmospheric data shows that the past of Venus was water-rich. We don't know if there were oceans, but it's likely that there was more water there. And finally, a very important question, especially if you think about now the discovery, the search of Earth-like exoplanets. We don't know if Venus and Earth had a similar geological history and diverged recently, or they were different from the beginning. And if they were different from the beginning, what does this tell us about the accretion and differentiation of these planets and what went on then? So there's a lot of important questions that we don't know the answer. So the interior of these planets, which is the focus of my work, what we know about the Earth is mainly based on seismic data from earthquakes that we measured. And on Earth, we know that the inner core that is solid and outer core that is liquid that generates the magnetic field on Earth. On Venus, the information we have is based on radius, mass, the tidal love number K2, gravity data, that's what I work on and I'm going to talk more about later. And a lot of information that we know about Earth, we kind of apply to Venus to kind of know what's going on in the interior. So we know that the Venus is also differentiated. There is a crust that we believe is basaltic from Venera, which is a Soviet landers from the 70s. There is a mantle that we think it's convecting, that there are signs of upwellings, so signs on the crust that something is pushing the crust from below. And so we have an upwelling, and some places we have downwellings where it could be an indication that there's like this cold spot where the crust is being compressed. And so there is some kind of convection going on in the mantle. And the core, we know it's liquid or partially liquid. We don't know the size exactly. And we know that it's not generating a magnetic field. And understanding the interior structure of the planet is not only important to understand the heat loss mechanisms and why there's no magnetic field and why there's no plate tectonics, but these are very important constraints on thermal and geological evolution model that people are running to understand how the planet geologically evolved from its beginning until today. So a brief overview on Venus exploration. So from the 60s to the 80s, there was a bunch of missions to Venus that was kind of ruled by the Cold War that was happening at the moment. And the history of Venus exploration is full of firsts in spatial exploration. It's the first successful flyby to another planet, the first probe to reach the surface of another planet, although it crashed, the first measurements of atmosphere, the first successful landing on another planet, the first successful photo from a surface of another planet. And these Venera missions that are the Soviet missions are actually all the information we have about the surface, the surface temperature, the surface pressure, and also the composition of the crust of at least the surface that we know is basaltic because of some measurements of these missions. So in 1989, NASA launched a mission called Magellan, which is the data sets I'm using are from this mission, so I'm going to talk about them more later. And more recently, there are mostly no missions to Venus. There was one in the 2000s, one in the 2010s, both to explore the atmosphere of the planet. Okay, so Magellan, it was a mission launched in 1989. In the first 2 years, it maps the surface, the geology of the surface, and using synthetic aperture radar images. So since it's the only way to map the surface because of the thick atmosphere. And in the second part of the mission, they acquired the gravity data. And what is gravity data and how do we measure this? So here is a quick example. In a gravity experiment, what they do is to use the communication of the satellite of the probe with Earth, and we know that there is a specific frequency, and when the spacecraft orbits around the planet, we'll have some Doppler shifts, right? Because there are some accelerations, and these Doppler shifts will be recorded as frequency changes on Earth. And here I'm showing the case for a perfect circular orbit on a perfect sphere. And here is a kind of a drawing of a real case where you have density differences that cause difference in the acceleration of the spacecraft. And we measure this frequency, small frequency changes that are related to actually local gravity anomalies that are related to the different density anomalies inside the planet. And that's what we work with. So here I'm showing the two data sets I've used the most is the topography and the gravity data. And what we can see is that where we have a high topography feature, we also have a positive gravity anomaly because of this excess of mass, right? And something else we can see is that sometimes we have some other high feature that has a positive anomaly, but is a less strong gravity anomaly than this one, for instance. And what this tells us is that the interior structure of these two kinds of features are different. And in fact, this is a volcanic rise. And this is what they call a Cresto plateau, which is the kind of feature I'm working on right now. And I'm currently writing a paper on that. But the important message here is that exploring if we explore the relationship between gravity and topography using a geophysical model, we can investigate the inner structure of planets and estimate some parameters like the crustal thickness, the density of the crust, and some other things. So we do this modeling procedure actually in the spectral domain. So, and since we are working on a sphere, we are talking about spherical harmonics, but that's not important. It's like a Fourier transform. Here we have the gravity coefficients and the topography coefficients that are related through this linear transfer function that is based on some geophysical assumptions that I'll talk more about later. So I'm studying Cresto plateaus, and they have some nice characteristics. The topography have steep sides, and it's kind of flat in surface, although has some wiggling because these are very deformed terrains that went through a long tectonic history of deformation, and this terrain is called tessera. Something else very nice that was discovered in the Venus Express mission was that these plateaus are associated with low emissivity anomalies. And this could indicate that the composition of these regions are different from the volcanic plains that surround them, and they could indicate that they actually have a composition more similar to a crust, to continental crust materials, like granitic material. And the formation of these regions is not very well understood. There are many possibilities. One is that it's a region of downwelling, so that there is the mantle convex, and there's some places where it is cold, these cold spots where the crust is kind of compressed, and then you can thicken the crust and make this high topography. It can be also an expression of mantle upwelling, so the opposite, where you have hot spots on the bottom. And it could be some other options is that it's coming from a massive impact of a big meteor that kind of melted everything and made these lava ponds that froze into these regions. And finally, that this is analog to continental crust, meaning that if there was an event on the past history of Venus that subducted, they recycled the crust, this would be regions that survived to this global recycling event. So what I'm working on is to try to constrain the interior structure of these features. And to do that, I considered that the outer shell of the planet, the mechanical outer shell that we call the lithosphere, behaves elastically. So when we put a load on top, a mountain on top of this lithosphere, how much it deflects in the presence of this load it's driven by a parameter that we call elastic thickness. So here we have an example of a very high elastic thickness, meaning that this lithosphere is deflects less, is stronger, and it deflects less in the presence of the load. And when we have a low elastic thickness, means that this structure is more compensated. And then we have a lower gravity anomaly related to that than in the case of a high elastic thickness. Another possibility is that these regions could, under these regions, there could be a subsurface load. So that's something else we consider, that if we have a buoyant layer, a low density layer under these regions, they could be, this topography could be supported by this kind of mantle plume or low density mantle layer. And we can also consider the fact when we have some, we also added the possibility of having intrusions in the base of the crust that can also give this type of signal here. So we consider all of these possibilities in our model, and we try to reproduce the observed gravity data with it. And so we try to estimate these three parameters: the elastic thickness, the crustal thickness, and this load ratio, that is the possibility of having something within the mantle that is actively having this topography. And yeah, so here I'm showing you the crustal thickness estimations that we found for the 6 regions that we study. And we showed the example with 3, okay, with 3 different loading possibilities. So the blue, dark blue stars are when we have the 3 free parameters that I talk about: the load ratio, the crustal thickness, and the elastic thickness. This crosses is when we fix the subsurface load to 0, so we only have the surface loads acting. And this last case is when we have an area isostasy regime, meaning that the elastic thickness is also equal to 0, and we have a fully compensated type of surface load. And what we can see, for most cases, these 3 parameters don't change a lot the crustal thickness estimations that we find. Although when we have 3 free parameters, of course, we have a higher error bar. And in fact, we cannot get a lower bound for the crustal thickness estimation. And when we don't have the presence of subsurface loads, we also get good estimations with smaller error bars. And in some cases, we also get a proper fit with an area isostasy regime with even smaller error bars. And this means that since we don't need actually the best fits are normally with no presence of loads, so only surface loads, and this indicates that the plateaus do not have an active support mechanism currently, so there's nothing on the mantle that keeps this high topography. It's basically the flexural compensation of the surface that supports this topography. It's a regime very close to this isostatic that we call area isostasy regime. And the crustal thickness estimations we find at around 20 to 30 kilometers are very close to what we have for the thickness of the continental crust on the Earth. The only different region that we have here is called Phoebe. And then in this case, when we do not add subsurface load, so this active support mechanism at the base, we have much higher crustal thickness values that we think are not quite correct, and it's kind of too high, and we think that this indicates that Phoebe actually have still active support component to its topography. And this is not so surprising because Phoebe actually have a lot of volcanoes around it, and there's this big rift valley that connects it to a big volcano up here. So it has some indications that it has like volcanism, and it has this heat source beneath it. So this is the main conclusion of this work, but a bigger conclusion that I want to point out is that there is a Earth-like planet in our backyard whose geological evolution is largely unknown, and it could really help us to, when we look at exoplanets, Earth-like exoplanets, to see if only based on radius and mass and size, if we can say if it's a Venus or it's an Earth. So it's very important that we understand what distinguishes these planets too much, if it's only based on this small difference between the distance to the sun. And it's time to go back to Venus to study its geology. And there's 2 missions, one from NASA and one from ESA, that might be picked this year to go to Venus, one in 2026. And ESA, of course, takes longer, 2032, to go to Venus and try to find out all these big questions that we still have. Thank you very much for your patience and to staying until now. the surface and subsurface loads. So the surface loads are the topography, right? They are basically, we see where we have in the topography data, we have a high topography. This will be defined as our surface load. So anywhere where we have a high standing topography. The subsurface loads is either, we consider two things, either something that is a negative density anomaly in the mantle. So when we have that, when, for instance, we have a mantle plume that makes it's hotter than its surroundings, so it's less dense, and this kind of makes the entire crust to go up and be supported by what we call an active support component, and not simply by the weight, and not supported by the weight of the flexure of the lithosphere itself, but this extra component coming from below. Another thing that we consider is we allow for the presence of intrusions in the crust. So when we have magmatism, like volcanism, we can have a volcano that spills magma on the surface, like a normal volcano, but we can also have magmatic intrusion. So we have some magmatism that is inside in the interior of the crust. And this is, we also allow to in our model. Is that clear? Okay, next question is about, we do expect seismic activity on Venus that could be measured to get information about the interior despite the absence of tectonic activity. Is it possible to estimate from a model the possible amplitude of seisms? So so on Venus we do not have plate tectonics, which is what we have on Earth, but we see signs of tectonism that there is stress going on in the crust. It does not make it like plates that collide into each other and subducts and make this like the Andes mountains, for instance, but there is some tectonism going on. So there should be seisms on Venus, like we're now measuring on Mars. So Mars is supposed to be a less active planet. We think it's a less active planet than Venus, and people are recording the Mars quakes. So it's possibly that it would be possible to record earthquakes, Venus quakes on Venus, quakes on Venus, but the problem is very technical because Venus is super hot. And it's hard to make a probe survive in the surface for more than days. And like this, to record seismic activity in a planet that is not as active as the Earth, we need like a longer time for the lander to stay there and recording this seismic activity, because it's not as active as the Earth, but we're sure that it could be, that definitely would be some seismic activity if we had the time to stay there and just listening. But I don't know, it's probably the people that work on the models that can know the amplitude of the seisms, but I'm not sure. Venus is very like unknown, so people really know really little stuff. I think Maria Chiara had a question.
Yes, but I'm too slow to write, so I prefer to speak. In the first slide, you show you compare the surface of Earth.
Maria,
sorry.
Okay.
Can you hear me?
Yes.
Yeah. Okay, sorry. I was saying that in the first slide, you compare the surface of Earth and the one of Venus, and you said that the one, the Earth one is older than the Venus one, but I'm sorry.
They are roughly. Earth is complicated because, as I said, there's these two types of crust. There's the oceanic crust that is much younger, and there's the continental crust. There are some parts that are much older, that like regions that we call craters, that we can find rocks that are billions of years old. But generally, the age of Venus and the Earth, we can say that it's like comparable. And and actually Mars, Mercury, and the Moon that have much older surfaces.
Okay, but also, I'm sorry if I say something wrong. Of course,
Go for
you
it.
can
Go ahead.
correct. You said that probably the Venus surface um, has something that make it more. I don't know if it is correct to say younger. I don't know. And I would like to know how can you observe this kind of different
How do
between.
you date the age of a surface of a planet?
Yeah,
Yeah.
exactly.
So the ideal thing would be to collect rocks and do some dating from uranium, like a decay of like we do on Earth, and as some from the Apollo astronauts got samples from the moon and also were able to directly date that, right?
Okay,
But we don't have that for Mars, for Venus, for
exactly.
Mercury, or for anywhere else in the solar system. Oh, besides, like now we have some asteroids that are these asteroid missions that are coming back, and it's very nice. But for the other planets, we don't have this direct dating of the rocks. So what people actually do is that since on the moon we have these heavily cratered surfaces and we have rocks from it, what people do to date planetary surfaces is to connect the amount they connect the amount of craters that they have in the surface of the moon and say that this is related to this age of the radiometric dating that they got, and this and then they kind of extrapolate this for the other planet
Okay,
based on the impact flux, the flux of asteroids throughout the time. They kind of can use some rules that they say, oh, if that's the age we have for the moon, this surface with these amounts of craters in this planet have this age. And in Venus, there's very little craters, and there's not very big craters, and that's why they said that the surface of Venus is very young.
okay, okay. Thank you very much.